Mr. Chairman, ladies and gentlemen, it's my great pleasure to present results of the research work concerning monitoring of rock bolt support systems as a way to improve safety in building and mining industry. The role of rock bolt support system is to secure and reinforce the rock zone in the near field of an underground opening, to fasten it to deeper rock strata. It may also be used in other fields, in civil engineering, especially in tunneling. Mostly steel rock bolts are used for that purpose. The rock bolt consists of a steel bar routed in an oversized hole. The portable installation machine is used to spin the bolt into the hole filled with fast-setting epoxy resin cartridges. After hardening of the resin layer, a plate and nut are driven up the bolt. So robust resin cartridges are used in mining practice. The rock bolt may not be fully encapsulated, the consequence of various geotechnical conditions like rock divergence, escape of grout into crevices, rock strata movement. There may be also technical problems which leads to improper grouting. So the lack of proper grouting is quite hazardous and should be monitored. There are many laboratories and research centers which have undertaken the problem of monitoring of such support systems. Different techniques may be used, among them using of ultrasonic gauges, also excitation of the structure to longitudinal waves. At the same time, different analytical approaches like wavelet transform analysis or neural network approach. In that method, I decided to use model analysis for diagnosis of this quality of installed rock bolts. Just to explain why. Generally speaking, mechanical structure may be described by three matrices of mass, stiffness and damping. And equivalent counterpart to that model is a modal model, which consists of matrix of natural frequencies and dampings and modal vectors. Rock bolt may be treated as an oscillator, and different lengths of and position of grouting change its forms, different border conditions, and since it changes its modal parameters. By proper extraction of these modal parameters, from which natural frequency is seen as more crucial, the proper identification of the position of discontinuity is possible. First of all, we should excite that structure to vibration, and in that approach, that structure was excited in perpendicular direction. It was revealed that the mode current in that range of interest, frequency range, is greater for bending modes than for longitudinal modes. And structure was hit using a model hammer with a force transducer placed in the head of that hammer, and the reference signal response signal was transmitted from accelerometer, which is placed on that outer part, sticking out part of this rock bolt. Then we measure frequency response functions using measurement setup. That rock bolt is hit in several points to get average results, to increase the accuracy, decrease the error, and eventually to omit node points. These are examples of stabilization diagram, which enables us to calculate these natural frequencies and waterfall curve for particular case. But what we need here is a reference model with which we may compare these experimental results. So such a model, finite element model, was built encompassing a large amount of cases of discontinuity, of course including different types of rock and growing. And these parameters which were used for that model were also checked experimentally, I mean rock parameters and growth. The resolution of this discontinuity was decided to was set as 5 centimeters. I assume that it's enough for proper identification of discontinuity, and the base of that cases with a resolution with different position and length of growing was built. So it's a model encompassing all these cases, and of course theoretical model analysis was performed to obtain these natural frequencies for these particular cases, and the aim of that comparison is to match this set of frequencies obtained experimentally with the base of cases which were calculated theoretically, and for that use also Trayon method, the cluster analysis was used. It's a nonlinear regression and distance of the lowest error between this experimental and theoretical models. So we look for that case which it's the best fit for this experimental results, best fit with a theoretical model. We have examples of this theoretical model analysis for particular cases. Measurement setup was also constructed and designed, developed. The first stage was a prototype version based on National Instruments elements, and then version which has to fulfill ATEXO requirements, because in coal mines we may also approach this explosive measurements in explosive atmosphere. So that new version fulfills that requirements. To validate that theoretical model, validation was performed on cases where that discontinuity was rooted in a controlled way, like experimental stunt, and first was performed without plate and nut, and after, because it's quite tough to remove that plate and nut in a real working conditions, so that both model and experiments were performed on this assembly, Hull assembly. Results from this experimental part with this validation enable us to validate that theoretical model. Here we have the example of frequency response function and position of this lack of grooting, which was, as I said, rooted in controlled way. Also, comparison between the prototype and new version was done, and as it was performed at a different time, so it also proves that of course here we have the same case, the same rock bolt. It's also proof for repeatability of that method. And we have scatter plots for this nonlinear regression and use of this cluster analysis for obtaining this. So we look for that matching or with a least error for this comparison between this theoretical and experimental model. Here we have another case which we analyzed. Also, comparison between just influence of pull-out test, or is it sufficient, was tested. It was in a different lengths of rock bolts were analyzed: 2.4 meters, 1.85, and shorter. and that assumption was to grout it in and the length of grouting was to be 30 centimeters. Pull-out test gave us information that even such length of grouting is enough for acceptance levels of that pulling out test. So it means that really this grout is quite strong, but it means that we can't check if that rock bolt is fully encapsulated using this method. Also, the measurements were performed before and after this pull-out test, so also kind of checking this accuracy and repeatability. Certain shift in frequencies were observed, especially in the highest frequency, probably increase in stiffness of this after the pull-out test. After that, normal testing was performed in a working coal mine. Was several session stages, and was in a working coal mine where this rock bolt support system is used. Among many cases, this is one of this example where lack of grout, that lower part of the rock bolt, and results the waterfall curve and obtained frequencies in comparison to between experiment and theoretical models. And the other case was lack of grout. Also investigate and obtained minimum for 90 centimeters. More dangerous case where we have a lack of grout at the end of rock bolt, so means that rock bolt is not anchored to this deeper part of the rock zone, and results for this case, matching of frequencies and scatter plot. Of course, we should also try to find out what's the reason of such not proper grouting, and to start with, we may say that the process of grouting of the installation of rock bolts into strata consists mainly of 4 technological phases. The first is placement of grout cartridges into a drilled hole using a rock bolt. Rock bolt is inserted up to its half length. Then is turning phase, with the continuous insertion of a rock bolt up to the end of the hole, and depending on the environmental conditions, time is about 10 seconds. There's a spinning phase, about 4 or 5 seconds, and the hold phase about 15 seconds. And much effort should be taken to control these phases, especially turning and spinning ones. Otherwise, grouting connection may not occur. Too rapid insertion of rock bolt may lead to leakage of grout from the hole, and lack of grout in the back part, close to the end of the borehole. Two long spinning face made the match contact between a rock bolt and the grout, also in the back part, close to the end. It's because hardening time in that part is shorter than it is in the outer part. The specific preparation of grout cartridges. Too slow insertion may result in not full mixing of grout, especially the end of rock bolt. I mean this lower part, and also may cause lack of grouting. Then problem is also with drilling methods and in hard rocks, that diameter of this hole may be larger than was projected, and because of that amount of grout inserted, it's not enough for proper connection of rock bolt to rock strata, and may lead to lack of grout in that lower part of that rock bolt. So these were probably the reasons for not proper grouting. These holes were also quite frequently inspected using cameras, so that case that holes are larger in diameter are not rare. Should that method maybe this non-destructive may be used in as a frequently manner, maybe repeated, let's say 1 month or in a certain periods, just to check. They use also statistical methods just to control 1 out of 10 or of more, to cover that bigger length of an opening. And as I mentioned at the beginning, it should be monitored for safety reasons. So that's what I wanted to share my experience, and I thank you very much for your kindness, attention, and I'm open for any questions. Thank you very much.